choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
I feel the liftoff. The clock has started. Roger. Godspeed, John Glenn.
Roger, 0G, and I feel fine.
This is a new and strange environment at first. This suddenly finding yourself in orbit.
We have a liftoff, 32 minutes past the hour. Liftoff on Apollo 11.
Houston, Tranquility Base here. The Eagle has landed. I'm going to step off the limb now. That's one small step for man, one giant leap for mankind.
Okay, Houston, we've had a problem here. This is Houston. Say again, please. Houston, we've had a problem.
Welcome home, Columbia. Beautiful, beautiful.
Discovery, go at throttle up.
Discovery, roger, go at throttle up.
Nose gear touchdown. Having fired the imagination of a generation, a ship like no other, its place in history secured, the space shuttle pulls into port for the last time. Its voyage at an end.
Hello and welcome. This is Michael Annis, and you're listening to Episode 3 of the Space Rocket History Podcast. And now, liquid-fueled rockets. During the late 1920s and throughout the 1930s, progress in rocket design was made in fits and starts with unclear goals. However, many technical advances in liquid-fueled rockets were made. The United States, Germany, Russia, France, Italy, and Great Britain all had rocket research programs. The most significant advances occurred in Germany, the U.S., and Russia. But before we proceed with the history, I want to explain how a liquid-fueled rocket works. As with conventional solid-fueled rockets, liquid-fueled rockets burn a fuel and an oxidizer. However, both of them are in a liquid state. A basic liquid-fueled rocket has two tanks and a combustion chamber. One tank is for the fuel and the other is for the oxidizer. The separate tanks are necessary because the fuel and the oxidizer will burn on contact. To launch the rocket, the valve for each tank opens, allowing the liquid to flow down the pipes to the combustion chamber. In order to create a stable thrust rate, a pressurized gas feed or a turbopump feed is used to move the fuel and the oxidizer. The simpler of the two, a pressurized gas feed, adds a tank of high-pressure gas to the propulsion system. The gas, an unreactive, inflammable, inert, and light gas such as helium, is held and regulated under intense pressure by a valve or regulator. The second and often preferred solution to the fuel transfer problem is a turbopump. A turbopump is the same as a regular pump in function, and it bypasses a gas pressurized system by sucking out the propellants and accelerating them into the combustion chamber. Whichever method used, when the liquids do come into contact with each other in the combustion chamber, they are ignited and thrust is created. Most of the early problems with liquid fuel rockets stemmed from a lack of cooling. The combustion chamber usually burned through after a short firing period. The material of the chamber was unable to withstand the heat of the burning gases, and the heat transfer to the coolant was inadequate. The solution to this problem was regenerative cooling. Perhaps the most significant event of the 1930s was the widespread use of regenerative cooling. Regenerative cooling is the process of cooling the walls of the combustion chamber of a rocket by circulating the propellant around the chamber before combustion. You may be asking yourself, with all the complications and difficulties associated with liquid-fueled rockets, why not just use solid propellant? Well, liquid-fueled rockets are the most powerful propulsion system available. They are also among the most variable. That is to say, they can be adjusted by a large array of valves and regulators to control and augment rocket performance. Liquid fuels can be throttled, shut down, and restarted, and that's the key advantage to using them over solid fuels. Okay, now back to the history. We will begin in Germany. In June of 1927, the Society of Space Travel, also known as the VFR, was formed. This group of mainly young scientists immediately began designing and building a variety of rockets. One of its members was an eager 17-year-old scientist named Werner von Braun. Von Braun would become a leader in German and later U.S. rocket development. His Nazi heritage made him one of the most controversial rocket scientists ever. Other prominent members of the VFR included Hermann Oberth, which we mentioned last episode, Walter Hoffmann, Willy Ley, Klaus Riedel, and Max Valier. Membership in the VFR quickly soared to about 500, a sufficient member base to allow the publication of a periodic journal called The Rocket. In 1930, the VFR set up permanent offices in Berlin and began testing rockets, which would ultimately change the nature of warfare and propel the world into the space age. These are the first humble tests begun at an abandoned German ammunition dump at Rickendorf, nicknamed Rocket Airfield. The true genius of the VFR team at this time was reportedly Klaus Riedel, although Riedel had no formal training. By August 1930, tests began on the first of the VFR rockets called Mirach, or Minimum Rocket 1. Powered by a combination of liquid oxygen and gasoline, Mirach 1 employed a 12-inch long liquid oxygen tank that shrouded a combustion chamber, thus cooling it. Gasoline was carried in a 3-foot-long tail stick. Mirach 1 was successfully static tested in August of 1930. During a second static test firing in September 1930, Mirach 1 exploded when its liquid oxygen tank burst. The cooling system was clearly inadequate. In the spring of 1931, the VFR tested Mirach 2, which was similar in design to Mirach 1, but incorporated an improved propulsion system. Like the Mirach 1, the Mirach 2 rocket was destroyed during a static test firing when its liquid oxygen tank burst. VFR then moved on to test a new series of rockets called Repulsor. It was named by VFR member Willy Ley. Repulsor rockets, like the Mirach ancestors, also burned a combination of liquid oxygen and gasoline, but the repulsor combustion chamber was cooled by water stored inside a double-walled aluminum skin. Repulsor 1 was successfully launched by the VFR to an altitude of 200 feet on May 14, 1931. Repulsor 1 just missed out on the honor of being the first European liquid-fueled rocket to fly. A few months earlier, Johannes Winkler built a 2-foot-long, 12-inch diameter rocket fueled by liquid oxygen and liquid methane. On March 14th, he launched his rocket to an altitude of 1,000 feet and took the title of the first European liquid-fueled rocket to fly. Now back to the Repulsor. Repulsor 2 reached an altitude of 200 feet and a range of 2,000 feet on May 23, 1931. Next, the VFR introduced a series of rockets under the designation of Repulsor 3. These were intended to be launched, then recovered intact via parachute. The first Repulsor 3 reached an altitude of 2,000 feet and a range of 2,000 feet. However, its parachute was torn off and the rocket crashed. Several Repulsor 3 tests followed with mixed results. These tests were followed by the Repulsor 4 series, which introduced a rocket incorporating a single tail stick for stability. In August of 1931, the first Repulsor 4 reached an altitude of 3,300 feet and was recovered by parachute. Subsequently tested Repulsor 4 rockets typically reached altitudes of about 1 mile. As a side note, I also wanted to mention that in 1931, Austrian Friedrich Schmiedel launched solid fuel rockets carrying mail payloads, primarily intended to be launched between the city of Schachel and Rotterdam, or Schachel and Kumberg. Schmiedel's innovative method of launching rocket mail was successful for several years. In 1932, membership with the VFR dropped dramatically. German police began objecting to rocket tests within the Berlin city limits. This was coupled with a fear of Adolf Hitler, who began restricting the activities of organizations like the VFR because they had significant ties to the international community. Facing total elimination, the VFR made pleas to the German army to aid in the continuation of rocket testing. In the summer of 1932, von Braun and his colleagues demonstrated a liquid-fueled repulsor-type rocket to the German army. The rocket crashed before the parachute opened, but von Braun was soon employed to develop liquid-fuel rockets for the army. He was allowed to continue experiments at the Army Proving Ground at Kummersdorf while working on his doctoral thesis in rocket combustion phenomena. In 1933, the first definite plans to construct a manned rocket emerged as part of the Magdeburg project. It was headed by German scientists Rudolf Nebel and Herbert Schaefer. A test rocket was launched on June 9, 1933, at Vollmerstedt near Magdeburg. Unfortunately, the rocket never left its 30-foot launching tower. Several tests followed with mixed results. On June 29, 1933, a rocket left the launch tower but flew horizontally at a low altitude for a distance of about 1,000 feet. This rocket was recovered undamaged and refashioned into a design more closely resembling the VFR repulsors. The redesigned rocket was eventually launched from Lindewerder Island in Teigler Lake near Berlin and reached an altitude of 3,000 feet before crashing about 300 feet from the launching tower. Additional test launches were conducted from a boat on Schowilo Lake through August 1933, at which time the Magdeburg project was completely abandoned. The VFR was having its problems too. During the winter of 1933-34, the VFR was forced to disband because it could not meet its financial obligations. Rocketry experiments ceased at the Rocket Airfield facility in January 1934, and the area resumed operations as an ammunition dump. Upon the disbanding of the VFR, all private rocket testing in Germany ceased. In 1934, the first new rocket was developed at Kummersdorf. It was called the A-1, which was an abbreviation for Aggregate 1. The A-1 was powered by an alcohol and liquid oxygen regeneratively cooled engine that would develop 660 pounds of thrust. After a few static tests, the A-1 was destroyed by an explosion caused by delayed ignition. A-1 was soon followed by the A-2, which employed separate alcohol and liquid oxygen tanks. The A-2 had a gyroscope located near the center of the rocket between the two fuel tanks. In December of 1934, two A-2 rockets nicknamed Max and Moritz were launched from the North Sea island of Borkum. Each reached an altitude of 6,500 feet. But the feasibility of effective military rockets remained speculative at best, exemplified by the fact that in 1935 Adolf Hitler rejected a proposal from Artillery General Karl Becker for a long-range bombardment rocket. This proved to be one of the Führer's critical mistakes. In April 1937, von Braun and his team relocated to a top-secret base at Peenemünde on the Baltic coast. The first task of the engineers was to develop and test a new rocket called the A-3. By the end of 1937, the Peenemünde team had developed and tested a 1,650-pound, 21-foot-long A-3 rocket, which burned a combination of liquid oxygen and alcohol. Although the propulsion system of the A-3 functioned well, its experimental inertial guidance system did not. The guidance problems were eventually solved and larger rockets were planned. By 1938, Germany had begun invading huge portions of Eastern Europe, and Adolf Hitler began recognizing the need for an effective ballistic missile weapon. The German Ordnance Department requested that the Peenemünde team develop a ballistic weapon that had a range of 150 to 200 miles and could carry a 1-ton explosive warhead. The size of the weapon would need to be compatible with existing railway in terms of tunnels and bends, and would need to be transportable in the field by truck. These criteria led directly to the development of the A4 rocket. An interim test vehicle to bridge the gap between A3 and A4 was named the A5. The A5 was similar to the design of the A3, but employed a simpler, more reliable guidance system and a stronger structure. The A5 was launched with the exterior appearance of the proposed A4. A5 tests were conducted from the fall of 1938 through 1939. The rockets were launched both horizontally and vertically, and were often recovered by parachute and launched again. The first A5 launch vertically reached an altitude of 7.5 miles. Now let's see what was happening in the United States during this period. In 1930, rocket enthusiasts met in New York City to found the American Interplanetary Society, the AIS. Conspicuously absent was Robert Goddard, the father of modern rocketry. Goddard did not publicize his advanced ideas, nor did he help other rocket researchers. As a result, most of the advances in rocketry in the 30s came from either Goddard or the American Interplanetary Society, both working separatively. In April of 1932, Goddard was able to launch a rocket with gyroscopically controlled vanes. The gyroscopically controlled vanes were significant because they automatically stabilized the rocket's flight. Meanwhile, the American Interplanetary Society completed the design of a liquid fuel rocket patterned after the VFR Repulsor series of rockets. It burned a combination of liquid oxygen and gasoline, and it was encased in an aluminum alloy frame. Fabrication of AIS Rocket No. 1 began on a farm in Stockton, New Jersey in August 1932. The first static test firing of the rocket occurred on November 12, 1932, at which time the 15-pound rocket produced a thrust of 60 pounds. A planned test launch of Rocket No. 1 was canceled on November 13, 1932, due to bad weather. Rocket No. 1 was never launched, but was overhauled and renamed Rocket No. 2. Rocket No. 2 was launched from Great Kills, Staten Island, New York on May 14, 1933. Its oxygen tank burst at an altitude of 250 feet. The AIS then planned tests using rockets 3, 4, and 5, which ranged in length from 5.5 to 7.5 feet and in diameter from 3 to 8 inches. Now let's take a moment and understand the difficulties experienced by the AIS rocketeers when they attempted to launch a rocket. First, due to the volatile properties of the fuel and the oxidizer, they had to load it into the tanks just prior to launch. The liquid oxygen had to be loaded by hand into a relatively long, narrow oxidizer tank. It sometimes took 15 minutes to empty a quart of liquid oxygen, and most of it evaporated from the furiously boiling supply in the funnel or splattered down the sleeves of the operators, inflicting tiny frostbites. The valves for the fuel and oxidizer tanks had to be opened by fuse wires connected from the dugout, which were a constant problem. And the remote firing control was a complete failure, leading the rocketeers to consider using a box of matches and a gasoline-soaked torch to light the fuse between the tanks of the rocket. Now back to the history. AIS Rocket No. 4 was launched from Great Kills, Staten Island, New York on September 9, 1934, and reached an altitude of 382 feet and a range of 1,338 feet. Rocket No. 3 was never flown due to a faulty design, and Rocket No. 5 was never built. The AIS continued to perform liquid fuel engine tests, but conducted no rocket launches through 1939, at which time all AIS rocket testing was ceased due to the advent of World War II. Now back to Goddard. In March of 1935, a rocket of Robert Goddard's exceeded the speed of sound. In May, Goddard launched one of his gyro-controlled rockets to a height of 7,500 feet in New Mexico. In 1936, scientists from California's Institute of Technology began rocket testing near Pasadena, California. This marked the beginning of the Jet Propulsion Laboratory, or JPL. The Smithsonian Institute printed Robert Goddard's most famous report, Liquid Propellant Rocket Development, in March of 1936. In 1937, Goddard watched one of his rockets fly to a height of more than 9,000 feet. This was the highest altitude attained by any of Goddard's rockets. In 1938, Goddard began to develop a high-speed fuel pump, or a turbo pump, to solve the fuel transfer problem we discussed earlier. And I would be remiss if I did not mention, in the same general time frame as the AIS and Goddard's activities, the Cleveland Rocket Society tested a number of liquid-fueled rockets that burned a combination of liquid oxygen and gasoline. These tests were conducted at a test site outside the city of Cleveland. Now let's see what was happening in Russia during this time. In 1930, Russian government rocket design teams led by Tsander and Glushko began testing a number of liquid-fueled rocket engines, burning such combinations as gasoline and gaseous air, toluene, nitrogen, tetroxide, gasoline and liquid oxygen, kerosene and nitric acid, and kerosene and tetranitromethane. Tsander published his work, Problems of Flight by Means of Reactive Devices, while Glushko published his work, Rockets, Their Construction and Utilization. In 1933, the Russians launched a new rocket called the Gerd-X. It was fueled by solid and liquid fuels. It weighed 65 pounds, was 8.5 feet long, and 6 inches in diameter. The first Gerd-X reached a height of 400 meters. The launch took place near Moscow. In November of 1933, a Gerd-X rocket reached a maximum altitude of 3 miles. In 1935, the Russians fired a liquid-powered rocket that achieved a height of over 8 miles. In 1936, another of the Russian rockets, called Avia Veneto, reached a height of 3.5 miles. It weighed 213 pounds, was 10 feet long, and 1 foot wide. And finally, in 1937, Russia established rocket test centers in Leningrad, Moscow, and Kazan. And so ends the liquid fuel rocket development of the 1930s. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.